Okay, and anyway, let's get started. So last time we talked about how to do inversely transform, and finished talking about some properties of some properties on the RLCs of the Z transform. And today we will talk about the properties of the Z transform itself. And once again, these properties will be a lot like what we have in discrete Fourier transform, and also be a lot like what we have in Laplace transform. So I think we will go through them really quickly. So first, as usual, we have this linearity. So if we have some small x1 of n and small x2 of n, then z transform to some big x1 of z and a big x2 of z. Then now we have a linear combination, this a x1 plus b x2, then they will z transform to a big x1 plus plus b big x2. And then we also need to think about what's the ROC of the resulting C. So ROC will basically be the intersection of R1 and R2, where R1 is the ROC of big X1 and R2 is the ROC of big X2. But just like in Laplace transform case, here we say it's containing the intersection between R1 and R2, because when you do this linear combination, some poles might be cancelled out. And when poles got cancelled out, your ROC can actually extend to something bigger than this R1 intersection R2. Okay, so this is just like in the Laplace transform. In the Laplace transform case, we have the same reasoning. This ROC containing intersection means that you will have at least this intersection. But if you cancel out some poles, then ROC can extend to a larger ROC. Okay. And a lot of the properties will have this flavor. So we also have time shifting. So if we have xn change to x over n minus n0, then you will z-transform to z minus n0 x times big X of z. So you get this extra z minus n0 term. This is usually what happens in this usual extra exponential factor happening in all the time shifting properties. And RC will be basically R, but you might have additional, you might add or delete something at the origin or infinity. So that's because, excuse me, because you have this z to the minus n0. So if n0 is positive, then you are adding, if n0 is positive, you have z to the negative power. Then z to the negative power, you have extra 0 at the infinity and extra pole at 0. And on the other hand, so if n0 is negative, then you have z to the positive power. Then z to the positive power is a pole at the infinity and 0 at the origin. Okay, so this extra z factor can change your ROC at the origin and infinity. Okay. So that's mark it in here. Yeah. We have this extra origin or infinity. Then we also have the scaling in the z domain. Next, we have the scaling in the z domain. So x of n z transform to big X of z with RCR. Then we scaling z with this z0. So we change from x of z to x of z minus z0. Then we get extra z0 z0 to the n on x domain. On the time domain. Okay. And RC will be multiplied by this absolute value of z0. Okay. And yeah. And this extra z0 absolute value also this this notation is the same as what we have in Laplace transform. So this region is related to this region by this kind of relation. So some point inside R, if and only if this point multiplied by this absolute value of z0 is also inside this absolute value of z0R. And so for example, if your absolute value of z0 is 1/2, then you are basically shrink your R to shrink your ROC to 1/2 its size. Okay. And here is a comparison of what happened. A similar thing in the a comparison of a similar property in the Laplace transform. So when we do Laplace transform, we were doing some time shift. We were saying we can do some S shift, so S changes to S minus S0. Okay. But now in terms of Z transform, Z is basically the exponentiation of S. So instead of shifting by some S0, we were dividing by some Z0. Okay. So yeah. So everything in Z domain divided by Z0, then in X domain you get Z0 to the N. And also if X of Z has a pole 0 and Z equal to A, then yeah, then then this is basically just Z shifting property. So we just shift is a Z equal to A point, we will shift to Z equal to Z0 times A. So everything get kind of rotated by this Z0. Okay. And the special case of this also will corresponding to will be the case where we do frequency shifting. So we multiply Z0 with a pure frequency. So in terms of Z, that will be e to the j omega 0 with some real omega 0. Then then the absolute value of Z0 will be 1, so your RC will not change, and you just will just rotate this whole Z plane by some angle omega 0. Okay, so x of n times e to the j omega n will Z transform to big X of e to the minus j omega 0 Z. Okay, and so we basically change omega to omega minus omega 0. So you just rotate everything on ROC by this omega 0. Okay, so this is a scaling in Z domain. Okay, this is a different scaling than we usually have. Usually, I guess this is, yeah, this scaling is corresponding to a shifting in S domain. But because of this exponentiation with Z, so we have a different form of scaling here. And next one is a time reversal. And once again, usually we have a time reversal. We have this kind of equation. We say we get a minus sign on t, then we also get a minus sign on frequency, or we get a minus sign on s. Sorry, minus sign on s. But once again, because of the exponentiation, so now we don't get a minus sign on z. So this is a different form here. We say we get an extra minus sign on n, then we do Z transform, then we actually get inversion on Z, so we get x over 1 over Z, and RC is 1 over R. Okay. And so this is a different time reversal than what we have seen in previous Laplace transform and the Fourier transform. But the idea is the same. The idea is basically S got a minus sign, the exponentiation S, you get this 1 over Z. Okay. Yeah. And so if it's 1 over R also means that if some point is inside the R, then 1 over this point is inside this 1 over R. Then next we have time expansion. This is a more complicated property. And once again, time expansion in the discrete case is weird. Okay. So we need to use this weird time expansion function we defined in chapter 5. So here is a small reminder. In chapter 5 we defined this x of n expand to power k to multiply by k, expand k times with this x sub k notation function. So x sub k of n is basically x of n but stretched out by k times. Okay, so it's x of n minus k if n is a multiple of k and 0 everywhere. And we have a schematic drawing, so we have some x of n here, and then you have k equal to 2, then you stretch out everything. Stretch out from this origin point by a factor of 2. So x of 0 is still f x of 0. Then this x of 1 will be located at this n equal to 2. then this x of 2 will be stretched out to this n equal to 4, etc. So this is this. So this is this x sub k function. Okay. And then using this time expansion function, then we can see how this time expanded function will behave in Z transform. And so here is our property, x of n Z transform to big X of Z. Then we stretch our x by k times to x sub k of n. Then Z transform will become, so Z transform will be basically you will compress Z by k times. So it will become x over Z to the k. And here we see the compression more clearly. So RC will be the origin R to the 1 over k. And so this is a bit weird. So say your RC RC was a circle, then this R to the 1 over k, your RC will be 1/3 of a circle. Okay. And yeah. And so x of z, it has a pole at x z equal to a, then x z to the k will have a pole at this z a to the 1 over k. Okay, and guess this is a bit weird, but because if you think about RC is a circle and you take the third root, then it's like 1/3 of a circle. But we also say RC should also always be composed of a set of circles. So what we do is we actually only change the absolute value of radius to the 1/3, and we still think it's a circle. Okay. So here we have an example. So say we have this x of z, big X of z equal to this 1 over 1 minus 3z minus 1, with RC being z greater than 8. Then then we do change. Then we do this change with k equal to 3. Then we change to this 1 over, change to this big X to over z to the k. Then so this z should have z should become z cubed, and so this 8z minus 1 become 8z minus 3. And so this pole at and so this original this original signal has pole at z equal to 8, but now because of this r equal to 1 over k, now this one pole actually becomes 3 different poles, because this z is now cube and it has 3 roots. So it has a root at so this 1 minus 8z minus 3 has 3 roots. It has a root at z equal to 2, and root at root at 2 times omega and 2 times omega squared, where omega is this e to the j 2 pi over 3. So you see that actually one pole at the original signal becomes 3 poles at the 3 poles at the new signal, and so RC still remains a circle, but so number of poles or zeros actually becomes 3 times, and RC is still remaining a circle. So RC was z greater than 8, but now RC becomes z greater than 2. Okay, so it's more complicated. Okay, so this is what happens when do time expansion. RC become, you take the case root of your RC. And then here is some interpretation of this result. So we can say big X of n, big X of z. This is just the z transform formula equal to x of n z to the minus n. I think this is basically a derivation. Anyway, big X of z to the k is x of n, then excuse me, z to the k to the minus n, and then it's equal to z to the minus kn. Then yeah, so this is basically a derivation, and then we do a change of variable. So we change from excuse me. So this method kn. So instead of summing over n from minus infinity to plus infinity, we can sum over from sum n from minus infinity to plus infinity. So n is every possible z power. So here the z power is only the power of z is only the integer multiple of k. But if we want to sum over all power of n, then we can say we only take n. We only take n where this n is take n. So instead of taking this n, we can take this n, and but we only have non-zero value of n where n is equal to nk. So that will be same as taking this x of n as x sub k of n. Okay. So this is basically a derivation of this result. Okay. And next property we have conjugation, and here we just show the result. I think the derivation should be pretty easy to get from just definition of the transform. So anyway, we do conjugation on the time domain. Then here this is not too different from Laplace transform. So we get a conjugation on the function and also get a conjugation on z. Okay. So yeah, so this is the result conjugation here, and here we have two conjugation. It's a big A star, Z star, and RC doesn't change. And once again, we also like to analyze the real signal. So for real signal, we have that x equal to x star, so big X of z equal to big A star of z star. Or the form we usually like more is we move this star to this side, so we have x of z star equal to x star of z. And just like the similar argument we have in Laplace transform, from this equation we see that pole 0 will come in pairs in the z domain. Okay. So if we have pole 0 at z, then we'll have pole 0 at z star. Okay. So yeah, so this is what happened. So point 0 will come in symmetric locations around your real axis. This is because, so say if your x over z0, if your x over z0 equal to 0, then x over z0 star will equal to x star of z0, which equal to this 0 star also equal to 0. Okay, so this argument has seen Laplace transform, so you should believe this. And next we have this convolution property, and once again this will be very useful for analyzing LTI system. And this property just look the same as usual. So you have convolution in time domain, you get a multiplication in the z domain. And then here we have the RC we need to be careful about. So RC will be intersection between those RC, but you might cancel some poles and get a bigger RC. And let's see some example. So now we have exactly what we said. So we want to use this to analyze the LTI system. So we have some output, discrete time output y, being the convolution of this impulse response and input signal. And here we pick a particular impulse response, h of n equal to delta of n minus delta of n minus 1. And this is particularly simple, so there's a difference between the two delta functions. And so we do a z transform on this impulse response, we get delta function will z transform to 1, and delta of n minus 1 excuse me, will z transform to z minus 1. And RC will be excuse me. So those two things, the signal is finite duration, so RC will be entire z plane, but you have a z minus 1, so z equal to 0 is not inside RC. Okay, and So at 0 you have a pole, and then also at z equal to 0 you have a 0. Sorry, z equal to 1 you have a 0, because well, 0 have 1 minus 1 equal to 0 here. Excuse me. Okay, and then we also do z transform on x. So we say if x of n z transform to some big X of z with some RLC, then we can think about what happened to y. Okay, so we have or small h equal to this, and z transform to this 1 minus z minus 1, and small x z transform to some big X, then we will have our small y will z transform to this thing times our big X, so 1 minus z minus 1 times big X. And RC will basically be the RC here, because our RC for our impulse response was the whole z plane, except at z equal to 0. Except at z equals 0, there was a pole here. So this pole might delete the RC at z equal to 0, and also you have a 0. Also, this thing has a 0 at 1, so you might remove a pole at z equal to 1 and extend your R. Okay, so that's the RC of y. And also, this system is a system we like a lot, because y is because we know delta function convoluted with our function has a very nice form. So delta of n is actually the system function. Excuse me, not system, it's the impulse response of the identity channel. So delta of n convoluted with x of n is just x of n, and delta of n minus 1 convoluted with x is just x of n minus 1. So this is actually the first difference of the signal x. Okay, and yeah, and so here we derive we also derive the z transform of the first difference. Okay, so if our system is we get the first difference of our input signal, then the z transform will be this 1 minus z minus 1 x of z. Now we think about now we think about other system that's the inverse of first difference. So we do accumulation or summation. Okay. So first difference is basically the differentiation in the discrete case, and here is a reminder of the differentiation in Laplace transform. So you have dx dt, then you get his. But you see that in discrete case, this is much more ugly. So instead of just having s, you have this 1 minus z minus 1. Okay. And similarly, we have that. And now we will do the parallel of the integration in the discrete case. That's accumulation or summation. Okay, so our system is now the rounding sum. Our system output is the rounding sum of our input. So W of n is the summation k from minus infinity to n x of k. And as we know, this is equal to this unit set function u of n convoluted with our input x of n. Okay, and now we do z transform on both of them, and then we get that. So first we want the z transform unit step function, and that will be this exponential decay function with a equal to 1. So that's 1 over 1 minus z minus 1, and then times this small x of n become big X of z. Okay. So yeah, so here we see the the output of the accumulation system in the z domain is this 1 over 1 minus z minus 1 big X of z. And then RC will be the intersection of the RC between x of n and u of n. And so that's RC of x of n, we just call it R, and RC of u of n will be z greater than 1. So intersection between R and z greater than 1. And we see this counterpart of this integration formula for the continuous time case. Continuous time case, we have this 1 over x over z, and also is the intersection between r and rex greater than 1. And yeah, here we have similar, so the algebraic part become 1 over 1 minus z minus 1 times big X of z, and RC is at least the intersection between r and z greater than 1. Okay. And next property, we have differentiation in z domain. And here we write this in a bit of a weird form, but I guess this is what happened. So we have a differentiation in z here, and but apparently that don't give us clean enough if we just have d big X of z dz, that don't give us nice enough equation. So we also need to put HRZ back here, and that will equal to minus n times 0x of n, or put a minus sign here. So we have nx of n will z transform to minus z dx dz, and RC doesn't change. And this formula can be derived from this definition of z transform. So you put d dz on both sides, and here we'll get on the left hand side you will get dx d big X dz, and on the right hand side we'll get dz to the minus n dz. So that's why we'll need to put the HRZ back, because when you put differentiation on this part of z, so first you will get a minus n, so that's why you get a minus sign and n here, and you will get negative 1 power over z on this side. And so if you want to compensate for that extra minus 1 power of z, then we multiply z on both sides. That's where we get the extra z here. And with the differentiation property, then we do what we like to do most. That is, I guess we can do many things. So first, we use this to rederive z transform that we derived before. That's the z transform of this log function. Okay, so we have x of z equal to log 1 plus a z minus 1, and with the RC being z is greater than a. Okay, and and we use a differentiation function. So we have nx of n will z transform to minus z dx dz, d big X dz. And now this log function, if we differentiation it with respect to z, then it becomes actual rational function of z. And if we do so log part, it will become 1 over this 1 plus a z minus 1, and there are extra factors. Yeah, and so if we believe that we sort out all the extra factors correctly, we will get those extra a z minus 2 etc. And combined with this minus z, we get this a z minus 1. Okay. And anyway, so we see that this z d big X dz actually become a rational expression, and then we can inverse the z transform this rational expression with our second method of inverse z transform. Okay, and actually, so I guess here there is a important trick that we use in doing inverse z transform, that we don't have such nice property for the inverse Laplace transform, is that we can use this time shifting property a lot. Okay, so if we are doing Laplace transform, then we want to start doing partial fraction expansion. We want to get rid of this z minus 1 factor in front, and we want to get totally some factor of like a clean factor of 1 over 1 plus a z minus 1 etc. But in terms of z transform, actually the the power of z in the numerator can be cleaned out very easily by just using this time shifting property. Because you see that here you have x of n minus n0 just equal to z to the sum power n0 x of z. So if there is extra power of z here, so this z to the minus 1, you can just plug in this formula. So this z minus 1 is just z to the minus n0 equal to 1. So this is just z transform to x over n minus 1. Okay. So yeah, so in terms of z transform, you can do partial fraction expansion much less, because the extra power of z you can just get away with this time shifting property. So this is a pretty nice trick you can use in z transform. And you can use the time shifting property to get rid of this power of z. It will make your life much easier. And so let's try to combine these things together. So we have that. So without this z minus 1 factor, so first we want to find the z transform of things without this z minus 1. So we have this transform pair. And this comes from our first example that we like most. So example 10.1, we have this a to the n u of n for z transform to this thing. And so we get extra a here, and also this was minus a here, so this a was actually minus a, so we have minus a here. Yeah. And then we use the time shifting property to get back our z minus 1 here, as we said. So we change n to n minus 1, so this n to minus 1, n to n minus 1, then we can get this extra z minus 1. And this is, so here, emphasize again, so this is a nice trick you can do, but also you can just do partial fraction expansion. You can still just try to divide this out and partial fraction expansion this in terms of z minus 1, then you can get the same result, but that will be a much harder calculation. Basically, you see you have a u of n minus 1, so this thing has a value only at n greater or equal to 1. And if you do partial fraction expansion, you will get a whole bunch of things starting basically with u of n. And so basically, you'll get a function with u of n and a function of delta of n. So basically what happens is at n equal to 0, you'll cancel out those two. Okay, and that's a longer calculation, but you should get the same result. And anyway, here we use the time shifting property to make our life easier without going into partial fraction expansion more. So we get extra n minus 1 here, extra n minus 1 here, and this corresponds to this thing. Okay. And now we compare this thing to this thing, and we see that on the right hand side we have what we have on the right hand side, and so on the left hand side this thing was nxn, and this thing should equal to nxn. So xn should be this thing divided by n, so that was this. So minus a to the n, and over n, and u over minus 1. Okay, so this is an example of using differential property to derive what we had in what we already derived in using the Taylor series expansion. Okay, and this is check out. And next we use the differential property to derive. As usual, we use this to derive what we need in the partial fraction expansion. So we derive this second order term. Okay. And for convenience, we also include az minus 1 on top. So we know we want to have the inverse z transform of x of z equal to az minus 1 over 1 minus az minus 1 squared. And as we know, this extra z minus 1, if your terms don't have this, you can also always correct it with the time shifting property. Okay, and anyway, let's see what how this goes out. So we get the the first order term, so a to the n u of n will z transform to 1 over 1 minus a z minus 1. And then we use our differentiation formula, so we have n a to the n u of n will z transform to, so we have this minus z and this in d dz. And d dz. And then we see that exactly we get this a z minus 1 over 1 minus a z minus 1 squared. And yeah, so this is why we want to include this a z minus 1 here, because make the expression much nicer. So here we have this a z minus 1 over 1 minus a z minus 1 squared, and the other side is just n times a to the n times u of n. Okay. Yeah, so this is the second order term we have, and once again, if you don't want this z minus 1, then you just change n to n minus 1 here, so you have a whole bunch of n minus 1. Okay, just like here. Yeah. I guess you need a plus 1 if you want to get rid of the minus 1. Because you want extra z on this side. Okay, but anyway, you can use time shifting to get rid of this z minus 1 if you don't want. Okay, so that's the second order term in terms of z transform, and also you can get a higher order term by the same logic. And now we talk about the initial value theorem. So sadly, we don't have the final value theorem for the discrete, this discrete case, this z transform, but we have an initial value theorem. So if x of this, so just like in the Laplace transform case, we need this basic kind of causality constraint. We need x of n equal to 0 when n less than 0. And then now the initial value theorem is very obvious. So if x of n equal to 0 for n less than 0, then then our x of z has only constant or negative power of z. Okay. So we have n equal to 0 term with x of 0, and all those negative power of z term with x of n greater than 0. And so if you take a z go to infinity, all these negative power of z will go to 0, and they will just left with this x equal to 0 term. So if x is this causal signal, so x is correspond to a causal system, then x of 0 will equal to z go to infinity x of z. Okay, and yeah. And yeah, so here we have, well, we use this be ambiguous causal sequence notation, but anyway, so if x of n satisfies this, then yeah, we have this thing. And yeah, and here we have a bit more derivation here. So we also say that if this thing is finite, and we can think about what happens if our x of z is expressed in terms of. So here we derive this by thinking x of z as a power series. But the other expression of x of z we have a lot is as a rational function, so rational polynomials. So n of z divided by d of z, and they want this rational function to have a finite limit. Then the order of numerator cannot be greater than the number of denominator. Otherwise, when z go to infinity, this thing will go to infinite. Okay, and let's see an example of initial value theorem working. initial value theorem working. So x of n equal to the 7 1 over 3 to the n u of n minus 6 1 over 2 to the n u of n. And when n equal to 0, this thing was 7 minus 6 should be 1. Okay, and now we have x of z is equal to this calculated result from before is 1 minus 3 over 2 z minus 1 over 1 minus 1 over 3 z minus 1 times 1 minus 1 over 2 z minus 1. So you can feel this factor come from this 1 over 3 and this factor come from this 1 over 2. And when z go to infinity, then all those 3 over 2, 1 over 3, 1 over 2 term cancel out, and it just has 1 over 1 times 1, and this is equal to 1. And it's consistent with our initial value theorem. Okay, and yeah, and so yeah, so here is a list of properties that we talk about today, and here we have HR mark where is R to the 1 over K. We still want the circle. We still want a circle ring because the RC of Z transform is always a ring. So actually we say R to 1 over K, we actually also means K copies of those pies. Okay, and then we also have some Z transform pairs. So I guess it's nice to see some of them. So delta function, as a reminder, will transform to 1, and the unit step function is a special case of this a to the n u of n, and it will transform to 1 over 1 minus z to the z minus 1. And delta of n minus n will transform to d to the minus n. So this is the same theory as the delta function. So delta function with a time shift will transform to power of z. Okay, and I guess two most basic cases we have is a to the n u of n will transform to 1 over 1 minus a z minus 1, and this with RC being outside a, and also this minus a to the n u of minus n minus 1 will transform to the same algebraic expression 1 over 1 minus alpha. Oh, this was well, I say it's a 1 over 1 minus a z minus 1 with inside RC. And also we have the second order term that we just derived, so we multiply HR in front, and we get the second order here, and the HR alpha d minus 1 on top. Okay, so those are the second order term that we can use to do inverse Z transform. And finally we have some sine and cosine. This can be derived by breaking sine and cosine into complex exponential, and you see that we have a quite complicated expression here. Okay, and I guess we have. Do we have a question so far? We are a little so. Yeah, I guess let's just review what we're going to do next time and stop here now. So we have BHR, that's causality and stability of the Z transform from the RC. And so causality, basically the system is causal if only if your RC is outward and including infinity. So this including infinity is the part where we are different from Laplace transform. Laplace transform, we actually don't have an equal if and only if condition. Remember that we say the Laplace transform, we say if it's causal, then RC was right-sided, but only if your system is also rational, you can get this if only if condition. But in terms of a Z transform, if you just have this including infinity, then you have a if only if condition for your causality. That's because back when we talk about the property, remember that this infinity was if only if your system, if only if your signal is 0 when less than 0. Try to find where were we? That was quite a long time ago. Yeah, this is property 4.5. Yeah. So here we already see that if only if x of n corresponding to a causal system, then our C will include infinity. Okay. And then stability is similar to the Laplace transform. So our system is stable if only if the RC include a unit circle d equal to 1. Okay. And for Laplace transform, it was including the the imaginary axis, j omega axis, and the j omega axis now corresponding to a unit circle. So the system is stable if only if the RC of the system function including this unit circle. Okay, and we'll see more details about causality and stability next time. And we'll talk about more about the transform next Monday. And then next week will be, I think it will be time for final. So we will try to finish what we want to talk about next week. And good luck on your final. Yeah. So see you next Monday.